Okay, so now we're going to cover section 1D. And remember, as I stated earlier, if you guys are in the spring 2021 class, I know later on I might use this lecture for a class in the future, but this will be the last section before the test for this class. So let's get going. Hold on, give me 1 second. I gotta, video's being kind of goofy on YouTube. Yep. Okay, cool. So let's go over 1D. 1D is actually kind of a fun section. It's on, actually 1D is on analyzing arguments. 1E, which we're not going to be able to cover, is on critical thinking in everyday life. Yeah. So 1D, we're going to analyze arguments. And to analyze any argument, really the first way to go about it is defining what kind of argument it is. And if it's logical in nature at all, it's going to be one of two arguments. It's either going to be inductive or deductive. Okay, so really it's defined by inductive or deductive reasoning. Your book uses the words inductive argument and deductive argument. Okay, hold on. Still clicking. So your book does two really good examples. So I'm going to start there, and then we can use these examples as we go along. So the first argument, which is kind of funny, it says, look, this is on page 41 if you're following along. It says, look, premise 1, birds fly into the air, but eventually come back down, right? They don't stay in the air. Premise 2, people who jump in the air fall back down. That's true. Premise 3, rocks thrown in the air come back down. Those are all three true statements, right? These are true statements. But then the conclusion says, what goes up must come down. Okay, this is a great example of inductive logic and an inductive argument. And your book defines inductive argument as so an inductive argument makes a case for a general conclusion from more specific premises. Each one of those premises was very specific, right? The bird goes up, it eventually comes down. That's a specific example. The human goes up, comes down, example. The ball goes up, it comes down. Those are very specific examples. So therefore, hey, everything that goes up must come down. So if we kind of thought of other examples of this kind of argument, if you think of one, you can butt in here and let me know. But let's think. Oh, I'll give you one. Now this is not true at all. I'm making this up. My neighbor, who is 70 plus years old, is very rude and is and then okay, so my neighbor who's 70 years old is really rude. My aunt, who is 75 years old, is really rude. I mean, rude. She's just rude. Okay, she doesn't have a filter. We love her, God bless her, but she's rude. Okay, and then my friend's grandfather, who's 80 years old, God, he's rude too, right? So therefore, look, those are the premises. Those are true. Let's say those are true. Okay, I know they're very subjective, but they're true. Well, then the conclusion might be, hey, anyone over 70 is just rude. Okay, right? That would be considered an inductive argument. Okay, an inductive argument, which of course we know is not true. There's people that aren't rude that are that old, right? And then same with the ball going up, or the what goes up must come down. It's not necessarily true, right? I think your book gives an example with a rocket. A rocket can go up and stay in the atmosphere or stratosphere. So therefore, it's not true. It can easily kind of be disproven. Those examples can. Now there are inductive examples that are more subjective, that are harder to be disproved per se. And I think your book will get into that. If not, we'll try to find one. Okay, but we need to know the difference though. So inductive means very specific premises. This person's rude, this person's rude, this person's rude. Therefore, all people are rude. Okay, the ball goes up, comes down, whatever comes up, comes down. Therefore, what goes up must come down. Okay, very specific examples. The other type of argument is deductive. Now, I'll tell you, deductive is more valid in nature. because it comes to a single conclusion. So your book says a deductive argument makes a case for a specific conclusion from more general premises. So it's a little different in that we're going to come to a very specific conclusion based on general examples, okay, or general premises. And the example that your book gives, an argument 2 on page 41 says, all politicians are married, which I don't think that's, let's just say it's true. All politicians are married, okay? And then premise 2, Senator Harris is a politician, okay? So if we know all politicians are married, that's a very general premise, right? And then we know that Senator Harris is a politician. Therefore, we can specifically conclude that Senator Harris is married, right? We're going from general premises to a specific conclusion. That is deductive reasoning. Okay, that's going to be deductive reasoning. Okay, and those are really the two different kinds. And I'm going to read this little blurb in here. It says, look, speaking more formally, we evaluate an inductive argument in terms of its strength. A strong argument makes the case for its conclusion seem quite convincing, even though it does not prove the conclusion true. Inductive reasoning does not prove truth, okay? Inductive reasoning doesn't prove truth. Deductive can, okay? Inductive cannot. Inductive is how we get bigotry, honestly, right? That is exactly how bigotry happens. You have a personal experience, and it's with someone of a certain demographic. Then you have another experience with someone with a certain demographic. And then you see something on the news with something with a certain demographic. Therefore, that whole demographic is a certain way. That is inductive reasoning, and it's false. Okay, it's not true at all. But our brains are very wired for pattern recognition, right? We're the greatest pattern recognition animals so far that we found. Okay, we have the best pattern recognition. But what can happen is that pattern recognition can get us into a lot of trouble. And one of the main troubles it can get us into, in my opinion, one of the largest troubles it can get us into is bigotry and making assumptions about people not based on truth, right? Not based on the facts. And one of those things is something of that nature, right? Where someone has an experience and therefore all are like that, right? For me in this town, I'm going to tell you, don't tell anyone else. This is very personal. But when I moved here, I did not realize how many old people were in this town. And I became really kind of, and I know I gave that example earlier, but I'll tell you, I got kind of, I don't know. I feel like around every corner, an old person was cutting me off on 62. And it really, like, I was like, oh my God, old people are horrible drivers, you know? And I really had to think, okay, no, Robert, you've had very specific experiences. And there's probably strength in that argument, right? That maybe the elderly are not as good with drivers. I mean, they have slower reaction times. Their insurance is higher for a reason, right? But there's no reason to conclude that all elderly drivers or older drivers are bad, right? So that's just something I noticed personally when I moved here. I don't know if you've had that same experience, but I know I had to kind of tame it down a little because it just started frustrating me more for no real reason. So anyway, that's a good example though that might happen in this town, right? Where we wind up having kind of these ideas based on very specific events and not more general events coming to a conclusion. Okay, so the book states, an inductive argument cannot prove its conclusion true. We just talked about that. So it can be evaluated only in terms of its strength. An argument is strong if it makes a compelling case for its conclusion. It is weak if its conclusion is not well supported by its premises. So you're not going to prove it right, but you're going to try your hardest. Now, this is like the court of law, right? I don't know, my head's getting crooked. The court of law is very similar, right? A lot of times you cannot prove that someone killed someone else or someone committed the crime, right? But you can make a compelling argument that it did occur. And so those compelling arguments are really inductive reasoning. Typically in a court case, it's inductive reasoning because it wouldn't get that far. If it could be deductive in how it was concluded, it's probably not going to make it to an actual law, a court, right? It's not going to make it in there where you have to go back and forth, because the jury would go, oh yeah, that's really easy to see that person did it because it was deductively proven. But inductive, though, the lawyer, on both sides, the lawyers have to make a compelling case, right, on innocence or guilty. So anyway, that's what that's talking about. The strength comes from that aspect. Your book then goes over 2 examples about hit movies and earthquakes, and they make good points. So it talks about like hit movies. If let's say you're wanting to make a hit movie, I'm going to make it more maybe personal in this town. Let's say you wanted to come up with a restaurant. You want to start a restaurant, okay? And in Mountain Home. Now I'm not sure if you guys are from Mountain Home, but I feel like there's turnover on restaurants in Mountain Home a lot. That's probably like most places, there's turnover in restaurants. So, but you're like, you know what? This is going to be different. This is going to be. It's not going to be a pizza place, which we've got like 2 brand new pizza places within a quarter mile of each other. But it's not going to be a pizza place. It's going to serve. Let's go. What would you guys want? We need seafood. That's true. It'd be scary to eat seafood in this town, but we definitely need seafood. So yeah, let's say we're going to go with seafood, Emily. So we're going to open up a classic seafood joint, not Captain D's, right? We're going to open up something that's a little fancier. And if we were going to make an argument for that, we could say, hey, look, specific. There's no other seafood restaurant in this town, right? That's a premise, right? That should be a good thing. Premise 2, hey, so there's no seafood argument. Maybe we went out and we surveyed the town, and it turns out people like seafood in Mountain Home, right? So there's no seafood restaurant. There's seafood in there's people in seafood, or people in Mountain Home like seafood restaurants. Premise 3, maybe we can have another premise. Let's say we've got we're going to pay the best seafood chef in Arkansas to come up here. Okay, boom, there's 3. So we're paying a guy or gal to come in and be the best seafood chef, or they're already kind of acclaimed to be one of the best seafood chefs, and we're going to pay for them. Now, can we definitively prove that this seafood restaurant is going to be successful? No, a pandemic might hit and we can't serve seafood anymore because we didn't set up for the pandemic, right? Or we can't, turns out, the cost to get the seafood in is just so high that it doesn't work out. So we can't prove that this seafood restaurant's going to work, but we can make a compelling argument by bringing in the ideas of why it should work. There's not one. The people love it. We've got a great chef to come up with a menu on it. Whatever that is. And if I'm not in the restaurant business. I'm not exactly sure. Maybe we've got a good spot on Highway 62. Okay. We've got a good spot that people want to come to, right? Location. It should work. It should make sense. It should be good. Okay. But then we can't prove that it'll be good, but we can make a compelling argument that it should be good. Okay. So that's one kind of good example of that's. Now remember, that's inductive. It's not deductive. It's inductive because we're trying to make our case on why it should be. Okay. Another one that your book goes over, which is, we'll go over this one, which is like the earthquake example, where some things happen in the past, and so therefore it should happen again. So I'm going to just read this one. It says, look, evaluate the following argument and discuss the truth of its conclusion. Geological evidence shows that for thousands of years, the San Andreas Fault has suffered a major earthquake at least once every 100 years. Therefore, we should expect another earthquake on the fault during the next 100 years, right? Now, this makes sense, right? This almost sounds deductive in nature, right? It's happened. The premise it feels like it's a general premise. Earthquakes happen. This earthquake has happened every 100 years. It should happen again, right? But it is very inductive in nature in that it's that, well, it should happen again, right? It might not. We don't know. I mean, the faults might have shifted and whatever. Okay, Mother Nature is just giving California a break. Okay, but we can't prove that it's going to happen in the next 100 years. It's just based on past experiences. Now, I'll tell you, and especially with relationships, past experience is the best predictor of future experience, right? Past actions are the best predictor for future actions. And you can use that one whenever an ex is trying to get back with you. Okay, but that's also inductive reasoning. Okay, that's inductive. It's not deductive. We can't prove that's actually going to happen because it's in the past, and yeah, it's a pattern, and that's great. That's that pattern recognition skills, right? But it can't be proven that it's going to happen in the next 100 years. It just has to happen. Okay. I hope that helps. Those are really good examples of inductive reasoning, and it happens a lot. I really this is something in this class that I hope you get out of whenever. God, maybe a little bit about yourself, maybe not, but if you notice that in yourself, things that you might have these feelings towards, like seafood, maybe, you go to a seafood restaurant and you got sick one time and you're like, or sushi, I'm not eating this crap again, right? I got sick this one time. I'm going to get sick every time I eat sushi. Well, really, you might just have bad sushi that one time, right? So, I mean, that's inductive. You might not get sick every time. Now, it might be safe just to not eat it again because you got sick once, but that doesn't mean that you've proven that you're going to get sick every time. Now, maybe if you had an allergic reaction, that's different, right? But if it was just a sickness, you might not get it a second time. Okay. So something. Now, there might be deeper things, of course, but I'm not going to go into that arena today. Okay, so the next type, which we mentioned before, is deductive reasoning. And deductive is so different because the premises which we're going to assume are true. I mean, we kind of have to with any type of argument, but with these premises, we can come to very specific examples that we can assume are also true. Okay, and your book, The Bubble, says, we apply two criteria when evaluating a deductive argument. The argument is valid if its conclusion follows necessarily from its premises, regardless of the truth of the premises or conclusions. The argument is sound if it is valid and its premises are also true. So if we can show something deductively and the premises are true, then our argument must also be true. Okay? So we have to assume the premises are true. And if they are true and we can follow something with deductive logic down, then we can assume our argument is also true. Okay, our statement is true. And your book goes over some nice bubbles there, but I want to get to the Venn diagram aspect because I do like the visual aspect. It's it's easier to kind of visually show these, the deductive arguments. And we can use the Venn diagrams again. It's called a Venn diagram. Your book calls it a Venn diagram test of validity. And I'm going to switch over to my my desktop camera. Section 1D. So the Venn diagram test of validity means we can do this with deductive because we're going to start with general assumptions. And your book does this, but I want to kind of show you that first one we talked about. So I'm going to go back. I'm going to look at these two premises about the politicians. Premise one was that all politicians are married. So we have to assume that's true. Of course it's not, but we're going to assume it's true for this argument. And premise two is that Senator Harris is a politician. A politician. And then the conclusion, of course, is that Senator Harris is married. Okay, so we're going to think of this with a Venn diagram, actually. We got to think of the groups here because these are general groups. Okay, so all politicians are married. Senator Harris is a politician, and Senator Harris is married. So I need to think of the biggest bubble first. And look, all politicians are married means that politicians are in the married bubble, right? So if we have all married types of people or groups, what we're saying is if married's here, politicians are in this bubble somewhere, okay? Politicians are there. So we've got, look, that's this first premise. All politicians are married. We can't have a non-married politician based on this example. Now, of course, that's not true again, but we have to assume it's true because it's the premise. Now, if I was going to make this argument in real life, I would throw it away because it can be easily proven false. Okay, but all politicians are married. Now, so that's the first premise visually, right? We got all married people. So married, non-married, right? We know how Venn diagrams work. We talked about this. And then you are lagging a little on my end. My Wi-Fi gets wonky when Weston or Emily, have I been lagging for you guys? No, okay, I bet, and she just got kicked out. I bet she's having the weather issues. Okay. Okay, so then we've got married, non-married, right? And then we got politicians, non-politicians. And politicians have to be in this married bubble. Now, the second premise, it says that Senator Harris is a politician. Now, because it's a single person, you can either write a dot or an X. Your book uses an X, so we'll just use an X. We'll use a different color we'll use blue. So we know that Senator Harris has to be right here because she's a politician, right? So therefore, the conclusion is that Senator Harris is married. Well, yes, look, if you're an X in the politician bubble, you have to be in the married bubble. So therefore, you have to be married, right? We can make that conclusion. This is deductive reasoning, okay? It's not little attempts at proving that she is, or he or she is married, but it's actually proving it with grouping, with bigger conclusions down to a specific conclusion, okay? Questions? So this is a visual way of doing it. I'm going to do visual way, and I think your book goes over a few of these. We're going to stick to the book examples. If I think of maybe a fun one, I'll use it too, okay? But let's look at another one. Let's say the book goes over a fish one. It says, evaluate the validity and soundness of the argument. So we're going to use these Venn diagrams to do that. The premise one, I just started using this marker. It should not be out. Let's see. Premise one is that all fish live in the water. Oh, that's true, right? All fish do live in water. I can't think of a fish that doesn't. Premise two, whales are not fish. Okay. If we're going to make that statement, we're going to make that statement. I could see where whales aren't fish, right? And then conclusion. You know where this is going. Whales don't live in water, right? Whales do not live in water. Well, this makes sense, right? If all fish live in water, whales aren't fish. Therefore, whales don't live in water, right? Well, look, this is definitely not valid, but let's show it visually on using a Venn diagram why the heck it isn't valid, okay? So I'm going to make my Venn diagram again. Let's think, all fish live in water. So therefore, if all fish live in water, then the fish has to be the small bubble for everything that lives in water, which is the bigger bubble, right? So we've got all things that live in the water. So water and land, and really there's like an in-between there too, right? Because I'm living both. But let's just say for this argument, we're just looking at ones that live in water and don't live in water, okay? And then we've got we got fish. Fish are right there. So this is visually premise one, right? All fish live in water, right? So we can say like habitat. So we got water, non-water, and then fish. All the fish are in there. Now look, whales are not fish. So what this means is whales are just not in this bubble, right? Okay, it's not in this fish bubble here. So therefore, whales do not live in. Well, no, you can't say that. Look, based on premise one, or really premise two, whales are not fish. Okay, that means by this logic, actually what we've shown, we haven't defined anything about whales being in water or out of water, okay? We could have, now I know we already know where whales live, but you got to think, based on these two premises, we haven't defined where whales live. We've only defined where fish live. Fish live in water. And then we just defined that whales aren't fish. So where we're at now, let's use the blue. This kind of makes sense. We can now, what we are supposed to do is draw a whale right here. Let's draw a whale. There's a whale. Okay. And really, technically, a whale could be in water or out of water. We haven't defined that based on these two conclusions. Okay. Now, we need another conclusion that said whales live in water, right? But look, we cannot come to this conclusion based on these two conclusions here. Okay. We have not stated that. We've only defined where fish live, not where whales live. Okay. And we've just defined that whales aren't fish. Okay, so it can't, look, this whale right here can't be in the fish bubble, but he could be in the water bubble or the non-water bubble. Okay, so be careful on how these are presented, if they're valid or not valid. So in this one, we would say this is not valid. I'm going to kind of read the lingo that they used here. So the conclusion states that whales do not live in the water, which means that X, now they used an X here. So the whale, X, represents whales should be outside the circle for things that live in water. But it isn't. It is on the border, meaning that we don't have enough information to know whether it is inside or outside the circle. Therefore, the conclusion does not follow necessarily from the premises, and the argument is considered invalid. Okay? This is considered invalid because the conclusion does not follow from the premises. Okay, the conclusion does not follow from the premises. Okay, questions? Okay, I'm going to do a funny one. I think I'm making this off the top of my head, but it's something my sons and I joke about all the time. Premise one. Robots are not living beings. Okay, well, robots are not living beings. Premise two, China has made bird robots. Okay, conclusion, birds are not real living beings. Okay, so if you jokingly heard the the statement that birds aren't real, we're going to show that that's invalid. You can Google it; it's funny. But let's talk about this, and I think I think this is a good and valid example. So first off, we can agree robots are not living beings. So let's look at the big bubble would be not living, right? Not a living being. So things that are not living, when I say living, I mean like, animals, things of that nature. Okay. And I should say robots are not animals. That would make this make more sense. So not living. And we know that robots are one of these things. Okay. You guys agree? Robots are one of these things. Now, China has made bird robots. Okay. This isn't a good example. Okay. China has made bird robots. What would be good Lord? What would be a better example? China has made bird robots. Oh, this isn't a good example. It doesn't go with what we're talking about. Dang it. China bird robots. Oh, okay. Well, let's think about this. China's made bird robots, but therefore birds are not real living beings. Well, bird robots are in here, right? We've got bird robots in here. We'll make that another bubble. But then to say birds are not living beings is not true because we haven't defined all birds. This is a horrible example. I just wanted to bring up the fact that birds are real and that this just isn't a good example. So let's just throw this away. Don't worry about it. If I can think of how to make that a good example, I will. But that's what I get for kind of thinking off the top of my head on this one. I'm trying to think here now. China, robots are not living beings. Yeah, no, it's just not a good one for the example we're going over. It might work later on, but not for this one. Okay, so let's look at another one. Invalid but true. Okay, this is an invalid but true. I'm going to stick to the book one so I don't mess this up here. Invalid but true. So it says, look, let's evaluate this. The premise one. All 20th century U.S. presidents were men. Say all. I'm going to say president, but let's know that that's U.S. presidents. Were men. Okay. Premise 2. JFK was a man. So conclusion, of course, JFK was president. 20th century president. Now, this conclusion is true, but our premises do not lead us to that, because I could have inserted myself in here, right? All 20th century presidents were men. Mr. Shirley was a man in the 20th century, right? Therefore, Mr. Shirley was a 20th century president. Of course not. So let's just visually see what's going on here, okay? So the first bubble, all 20th century presidents were men. So therefore, we've got the men bubble and the non-men bubble. So we've got men, and then inside that men bubble, there's a group of 20th century presidents, right? 20th century presidents. Now look, the second premises just says that JFK was a man. That's all it says. So if JFK is a man, he could be either in the 20th century president bubble or outside of the 20th century president bubble. Like, imagine it just said X person was a man, not JFK. It said X person was a man. Well, that doesn't mean they were president. They could also be out here. So therefore, if JFK was a president, we'd have to put him kind of in between here, okay? The way they've defined JFK. Now, we know, of course, he was a president, but we can't get to that conclusion from their premises, okay? We cannot get to their conclusion, that conclusion from their premises, okay? Questions about that? So it is considered, yeah. The argument is therefore invalid. Look, the argument's invalid even though, you know, its premises and conclusion are true, because we're not getting to it. I mean, gosh, that's like, it's just really bad logic. Okay, but visually, that's what's going on here. Visually, that's what's going on here. Questions? We keep kind of rocking and rolling here. I'll tell you, it is a little easier when you can make Venn diagrams to show if deductive reasoning is true or not. And again, this is still deductive because it's broad conclusions, right? Bigger conclusions, or bigger premises, I should say. So the next type of argument is the conditional deductive argument. Now we've kind of been doing that already, but it's an if-then statement. Okay, it's written in an if-then way. If this, then that. Okay. And then your book goes over kind of a diagram. I'm not going to necessarily go over that, but we're going to talk about examples with this whole if-then stuff. The first one that your book goes over, or just as an example, says the premise is that if a person lives in Chicago, then the person likes windy weather or windy days. If a person lives in Chicago, then the person likes windy days. Now we're going to assume this is true because it's a premise, okay? Now we know that's not necessarily true, but we're going to assume it's true because it's a premise. And let's just draw what that is telling us. So if a person lives in Chicago, then that person likes windy days. So therefore, we got to think about this. So people that like windy days, all Chicago people are going to be inside that, right? So we're going to say likes windy days. So these are all the people that like windy days. And, outside this bubble are people that do not like windy days. And then we've got Chicagoans, okay? Right here. Chicago. Okay? People that live in Chicago right there. Okay? That's what the first premise is. Okay, second premise. Carlos lives in Chicago. Okay. Hey, if we know that Carlos lives in Chicago, he's got to be right here somewhere, right? And therefore, we can make conclusions about Carlos. Therefore, Carlos does like windy days, right? And that's what it says. Conclusion, Carlos likes windy days. Yeah, that's definitely valid, the way we've written it. But this is that if then, the conditional deductive reasoning. If something, then something else, okay? Your book kind of breaks it down with like an if P, then Q type statements, and it being valid or invalid. And for this one, it's look, if P, then Q. So if a person lives in Chicago, then the person likes windy Cindy's. Then P is true. Then Q also has to be true, right? That's a valid statement. Okay, it's kind of goofy. It's really a lot easier to grasp just by working the example through than by creating the table. Like on page 46 at the bottom, if you're following along in the book, on the bottom of page 46 is the table. And it kind of goes through the valid and invalid aspects of conditional deductive reasoning. And we'll go through a few of these, okay? This is one that's definitely valid. So this is, of course, the if P then Q, then P is Q, Q is true type statement. So let's look at an invalid one with the if then. And again, I'm just working through the examples. So it says use a Venn diagram. This is example 6 on page 47. Use a Venn diagram to test the validity of the following argument. If an employee is regularly late, then the employee will be fired. If the employee is regularly late, oh Lord, I spelled that horribly. So if that's the premise, if the employee is regularly late, then the employee will be fired. So premise 2, actually, let's draw that one. Let's draw premise 1. Okay, let's think about this one. So if the employee is regularly late, then the employee will be fired. So, okay, so therefore we've got the people that are fired and not fired, right? So we got fired and hired or not fired, right? So we have people that are fired and the people that are not fired. Well, if the employee is regularly late, they're definitely going to be fired. So we've got, let's put late bubble. If you're late regularly, you're going to get fired, okay? Now, premise 2 says Sharon was fired. Oh, Sharon. So we know that Sharon was fired. Ah, crap. Conclusion, Sharon was regularly late. We can't assume that, right? Just because Sharon was fired doesn't mean she was regularly late. We can't jump to that conclusion. That's not fair to Sharon. Now, visually, the way we would say that, of course, is with where Sharon's at in the fired bubble. Remember, she was fired, right? But where she's at in the fired bubble, she could have been late or not late. So we're going to put her right there on the edge. She might have been late. We don't know. Maybe that is true, right? This isn't stating anything about her being late. It's just saying that she was fired, okay? So this is definitely an invalid conclusion. Now, it might be true. We don't know. We don't know what Sharon's work ethic and habits are, but We cannot come to this conclusion about Sharon based on these two premises. Okay, we cannot come to that conclusion based on these two premises. So therefore, this would be considered invalid. Okay, it would be considered invalid. Question? Let me know. And I am just doing the ones right out of the book, but I'm hoping to give a little more than what the book is kind of telling you. So example 7, which is denying the hypothesis, it's the third one. Okay, I guess I could have gone along with this one. So that last example we did is affirming the conclusion, which is invalid. The next is going to be denying the hypotheses. So let's look at this one. We've got premise 1. If you like the book, then you'll like the movie. I'm going to draw that. If you like the book, you'll like the movie. Okay, so, okay, you got to think, if you've noticed a little pattern here, the then statement has always been the big bubble. Okay, you like the movie. Of all the people that like the movie, like the movie, don't like the movie, right? The Venn diagram is really distinct here. You either liked it or you didn't like it. Well, what we're saying is if you like the book, then you'll like the movie. So therefore, you like the book. This is what that premise is saying, right? Hey, if you like the book, then you're definitely going to like the movie. Okay, you'll be in that bubble. Okay, so the second premise is that you did not like the book. Okay, you did not like the book. So look, you're not in this bubble here, right? You didn't like the book. You read the book. You're like, this book is garbage. So you're just not going to be in this bubble in the yolk. If you think of it like an egg, you're not going to be in that yolk right there. The conclusion: you will not love the movie. So the conclusion is you will not love. Oh, I use love and will not like. It's okay. The movie. They use. Oh, they use love right here. We'll just use like to be consistent. You will not like the movie. Okay, well, that's not necessarily true. Just because you're in this bubble, you didn't like the book, right? Doesn't mean that you're going to like the movie or not like the movie. Now, again, we'd have to put an X right here. You could be in the like the movie group or outside of the like the movie group. We're not defining that at all, right? We're not defining that at all. Okay. Questions? Comments, concerns? So that's considered denying the hypothesis. It's on the bottom of page 47. Now the last one is denying the conclusion, which is true. So let's look at this one. So we've got an example here. Let me look. So premise 1. A narcotic is habit forming. Okay, a narcotic is habit forming. So we've got all things that are habit forming. And we're going to say that narcotics are in that bubble. Okay, that's what the first permit says. We've got a narcotic, or we're stating a narcotic is habit forming. So therefore, all the things that are habit forming are right here, and narcotics are squarely in that, based on that premise. Premise 2, aspirin is not habit forming. Okay, well, if aspirin's not habit forming, it can't be in this bubble. So I can state right now, aspirin's out here, right? Because it's not habit forming. So the conclusion is that aspirin is not a narcotic. Yes, we can conclude that. Aspirin is definitely not a narcotic, but we can get there from these two premises, right? If a narcotic is habit forming, so therefore it's in the habit forming bubble, right? It has to be. So it can't be in or out. It can't be both. It's got to be in. Aspirin's not habit forming, so it can't be in the bigger bubble, right? It's got to be out here. Well, therefore, there's no way for it to get into the narcotic bubble with these two premises, okay? With these two premises, there's no way it could get in the habit bubble. I can give you a good example of this one off the top of my head, right? Okay, hold on. Premise 1, Baxter County is in Arkansas, right? So, or you could say a Baxter County resident is an Arkansan, right? So if we've got AR out here, all the people in Arkansas, we know that there's a portion of them that live in Baxter County, and they are definitely in Arkansas. So if you're in Baxter County, then you're in Arkansas, right? Premise 2 is that, let's say, a Chicagoan. No, it's not Chicago. Let's say Robert is not in Arkansas. So Robert's not in Arkansas. Oh, so he's got to be out here somewhere, right? So therefore, we can conclude he's not in Baxter County, okay? Okay, so Baxter County is not in Arkansas, right? You guys agree. Robert is not in Arkansas. He's out here. So therefore, Robert is not in Baxter County. That's a valid conclusion. And this is considered denying the conclusion, okay? We're denying the conclusion because Robert is not in Baxter County. Okay? It's a denial rather than that first one that was valid was a conclusion, right? It was affirming. Yeah, affirming the hypothesis. Cool. Well, yeah. Your book goes over the inductive and deduction in mathematics. And this is important. This would be more important if we're going on to like an algebra class. But look, if you're going to inductively test in math, it's when you use examples. So yeah, we'll go over this just a minute. If we were going to use examples to show something, that would be in an inductive way of showing it. So let's look at rules. I think your book goes over the commutative rule of multiplication. Let's look at a different commutative rule. Let's say that you wanted to show the commutative rule. I'm not going to make you memorize these rules, but commutative rule of addition. And you wanted to show that it was true. Now, the commutative rule of addition says this. If we have A plus B, it equals B plus A, right? It doesn't matter what order you write this in. Now, to show this rule inductively, you can just choose numbers to plug in to show that it's true. So to show it inductively, you use examples. So let's say I said A equals 5 and B equals 7, okay? So I'm going to plug that in, 5 plus 7. And I want to know, does it show equality? Will 7 plus 5 be the same thing, right? If we're plugging in, well, yeah, 5 plus 7 is 12. And that's equal to 7 plus 5, which is also 12. So that shows it. Now, look, this is inductively showing it. You haven't deductively shown it. You've inductively shown it because you've used an example, okay? You've used an example. Therefore, it's inductive reasoning, okay? let's see here, suppose. Yeah, okay. Well, I'm going to kind of go through your homework a little bit and see if I can see different ones. Oh my Lord. Determine the truth. Okay, look, I'm looking at number like 23 in your homework. It's on page 52. And it says, we've got a few premises here. Premise 1, 2 plus 3 equals 5. That's true, right? Premise 2, 5 plus 4 equals 9. Also true. Premise 3, 7 plus 6 equals 13. I would say all of these are true premises, right? So conclusion. The sum of an even integer and an odd integer is an odd integer. This is clearly inductive reasoning, right? I think they even kind of state that to begin with, but this is clearly inductive argument, okay? Your book uses the word argument. This is an inductive argument because these three premises are examples, right? 2 plus 3 was 5, 5 plus 4 is 9, 7 plus 6 is 13. These are examples of an even integer, for here 2, 4, 6, and an odd integer being added to it, and it equaling an odd. So there's just 3 examples of it. So the question states, determine the truth of the premises of the following arguments, then assess the strengths of the argument and discuss the truth of the conclusion. Now, you know what? I'm going to see how they want you to answer this, because this is interesting. And, I do the odds so you guys can see the answers in the back for this reason. 1D, this is number what, 23. Yeah, I mean, well, the premises we said are true, right? And then it says the argument's moderately strong, right? I mean, yeah, the argument is, that's very subjective, and you won't see it written like that on the test. I don't like the way that part is saying about the strength of the argument, but we can discuss the truth of the conclusion. Now, remember, we can't prove this based on inductive reasoning, so we can't prove that this conclusion is true, but we can know, is it true or not? If you add an even to an odd, would you always get an odd? Well, yeah, that is true. I can show you how to prove it here in a minute, which is kind of neat, and you don't have to know how to prove it, but yeah, that's a true statement, right? If you ever add an even and odd together, you always get an odd. 2 evens will give you evens. 2 odds, what will 2 odds give you? It's always even, right? Yeah, it's always even because you're multiplied by 2. But when you add an even and odd, you always get an odd. So this is a truthful statement, but getting to it based on these premises is pretty weak. Now, how would you show this to be true? Well, I'm going to kind of show you a basic proof here. We're going to start with n. And this first n is going to be any even number. We're going to define n. So our first premise really is that n is any even number. Well, therefore, n plus 1 would be any odd number, right? You guys agree with that? If n is any even number, you add 1 to it, and you've got any odd number. So like if n was 5, well, 5 plus 1 is 6. Oh, wait, no, it's an even. I'm sorry. If n is 6, then 6 plus 1, that's odd, right? So now it's saying the sum of any even and odd is also going to be an odd. So if we add these together, n plus 1, we wind up with n plus n, that's 2n plus 1, right? Well, I'm going to tell you this is also an odd number. Like if we chose 2 times any number is going to be even, right? If you multiply 2 by anything, 2 times 5, 4, 3, 2, 1, doesn't matter. If you multiply anything by 2 and n by 2, I said any even, any even, let's see, integer. I shouldn't say number. That's going to be even. Well, then you add 1 to it and you wind up with an odd. Okay. So this is how we would prove it deductively. You do not have to know how to do this. Okay. But the reason this is deductive is because we're not using specific numbers. We're using general number. We're saying n could be any even integer, right? And n plus 1 is any odd integer. Should have said it like that. So we can't do fractions and stuff. So therefore, when you add them together, you wind up with an odd. Again, you don't have to know this, but this would be the deductive way because you are not using specific examples like we did up here in 23. Okay. Great. Great. Okay. So for the homework, now we can get into the schedule. So the homework for today, which is 1D, page 52, is 1 through 71 odd. Okay. 1 through 71 odd. Work on those. If you have questions, let me know. I mean, the test is going to be Wednesday, so you need to get done as soon as you can. Do you guys in the class have any more questions? I'm going to bring it to me here. Have any questions? I'll wait around a little bit. It doesn't look like it. Okay, I'm going to stop the video. So remember, if you're in the class this semester, if this is spring 2021 semester, your proposals due Monday, and the test will be, I'm sorry, Wednesday. The proposals due Wednesday, and the test will be open Wednesday as well. And remember to watch the video on the test one on the introduction, or the